Coming to carbon fibers. Carbon fibers have attracted a lot of interest in automotive applications these days. So, what are carbon fibers? Why are they so special? Right now, is the science and technology of carbon fibers new? Absolutely not. Carbon fibers have been in existence since 1960s, and predominantly over the several years they have been used in aerospace applications. A classic example is 787, right? But so in aerospace, carbon fibers is not new, but in automotive, carbon fibers have been attracting a lot of attention because of their outstanding stiffness and strength. So what is special? If the science and technology of carbon fibers in aerospace is already well established, what is so special of being applied them to automotive? Well, there is a big difference, or maybe two differences. Number one is carbon fibers are expensive, and aerospace can actually afford expensive materials because aircrafts are very expensive, right? But can we use the same expensive materials in automotive? Absolutely not, especially because the margins within automotive sector are so less, right? So you have to find an affordable way of making these carbon fibers for automotive applications. And then the second thing is availability, right? For availability and manufacturing method. So the carbon fiber process that's implemented in aerospace has a long manufacturing cycle. So, but they're okay with that because at one point they used to make one aircraft a month, but these days they make one aircraft a week. That is still acceptable. But if you talk about automotive, you make several hundreds and thousands and millions of vehicles in a year time frame. So pretty much if you actually take the case of Ford F-150, every 6 minutes, actually less than that, is when you can get one vehicle out. So that means the cycle time has to be very, very, very fast. So these are two challenges: faster manufacturing time and or lower cycle time and lower cost. These are the two challenges of implementing carbon fibers directly in automotive applications. So these are the two major applications that you need to work upon, right? So with these two challenges, how do we go about these carbon fibers? Understanding the carbon fibers for multiple different applications is basically what we are going to study in this. So you can see that again, as I said, in 1960s, since 1960s, the science and technology has been well established. But in 2015 and beyond, the automotive sector has started looking. In 2000s is when the automotive sector has started looking into these fibers quite a lot. So let's look at carbon fibers. So unlike glass has some materials like silicon dioxide on sand plus metal oxides that are melted, and then eventually you draw fibers from it. In carbon fibers, you actually have to start with a completely different precursor material, right? Or even polymeric fibers, right? Let's say you melt the polymer and then you can draw the fibers. But in carbon fiber case, you actually have to completely start with a different material. The prime reason is carbon is an element which you cannot melt. So that is why you actually use a precursor, draw the fiber, and then you carbonize it. So what are the different precursors that are used in the making of carbon fibers? There are three precursors that are used: polyacrylonitrile, or PAN, which is the most popular form of precursor that is used in the making of carbon fiber. And the second one is the pitch, which is a derivative of the petroleum process. And then cellulose, these days, again, lignin is another precursor material that is used in the making of the carbon fibers. So let's look at the PAN or the pitch process. So first what you do is you take the polyacrylonitrile, which is a polymer, or even the pitch, and then you make a fiber out of it. And once you have that fiber and you put it in a rowing form or whatever, and then you pass that through the carbonization and graphitization process to make the eventual carbon fiber. First, it passes through a stabilization in air where it is subjected under high tension. And that basically provides the directionality and orientation of the molecules, which eventually dictate your carbon fiber properties. And this is done at 200 to 400 degrees centigrade, and subsequently it is sent to carbonization process, which is subjected anywhere between 400 to 1400 degrees centigrade. So why this temperature range? Because each and every temperature will provide different types of properties for the carbon fiber, and the cost also changes. Just remember this point, and we'll talk about the cost in a minute. And after the carbonization, it goes through the graphitization, which is subjected anywhere between 1900 to 3000 degrees centigrade. After that, you have electrolytic bath, washing, sizing. Sizing is nothing but giving some kind of chemical functionality, and eventually drying that and then transforming that into a spool. And now it's ready for deployment for making it into a composite. Okay, so just remember the process: stabilization, subjecting it to high tension and continuing the tension, carbonization, graphitization, and then the post processing. Once it's after the graphitization, it's nothing is changing chemical structure wise, but chemically you're making some changes to make it adhere to the eventual plastic that you're working with, or a polymer. So the oxidation process, which is basically the second part, right? It is actually adding some functional groups so that you can size the material for certain for compatibility with certain polymers. Because remember, in the very beginning we talked about the fiber and the polymer. If there is no good compatibility, there will be an interfacial gap. So achieving a good compatibility, you have to size this fiber so the surface of this fiber is compatible with the polymer. And this is basically what's happening in the electrolytic or oxidation process, and eventually in the sizing step as well. Now, let's look at the different carbonization as well as the graphitization process. What's happening in the carbonization as well as the graphitization process is that the density is increased from 1.2 to 1.78 grams, with changes occurring more or less uniformly throughout the process. So the diameter is decreased. Why the diameter is decreasing? Primarily because you have this polyacrylonitrile backbone, and then you have all these carbon hydrogen atoms bonded together, right? Because it's a hydrocarbon material. Now, when you have a carbon fiber, you wanted a pure 100% carbon fiber material in it, just pure 100% carbon in it. So the hydrogen tends to go out. You don't want the carbon to go out and eventually form it into a carbon dioxide. So that's why you tend to retain the carbon by putting it and doing this whole thing in the inert atmosphere. But you want to remove the hydrogen. So the more carbonization and graphitization process, the longer you do subject it to, again, polyacrylonitrile also has nitrogen. So you want to remove the nitrogen as well as the hydrogen as well. So the higher temperature you subject this to, and the longer you do it this for, you will remove more nitrogen atoms, more hydrogen atoms, and that will impart more, that will require more energy, and the cost goes up, and of course the cycle time also goes up, which definitely means that your cost of the fiber significantly enhances. But the more pure form of carbon you have, the higher will be the property. So if you remember, we talked about carbon fiber being standard modulus, intermediate modulus, and ultra high modulus. So between all these three, it is the amount of carbon content that is there in the final fiber that is dictating the different types of properties as well as the cost associated. Because for the standard modulus, you may get it like in $10 to $20 per pound, and then intermediate modulus may be around $20 to $30, and then ultra high modulus much significantly higher than that. And each of them will have a specific application requirement when it comes to automotive or aerospace. And you can see these are the properties that we are talking about. As you can see, that the tensile modulus between standard, intermediate, and ultra high is significantly changing anywhere between 230 to 270 to 400. And that is for the pan based, and for the pitch based, it's anywhere between 300 to 700. And Rhine is nothing but the cellulose based, which is again one of the lowest. These days, a lot of research is being done into lignin, because whether it's a pan, pitch, or cellulose, the cost of the precursor is pretty high. So that particular part you cannot change, right? That's a precursor, you're getting it. And this process is something which you can work upon in terms of developing a low cost or a high cost carbon fiber. But if your starting precursor material is actually very less expensive, then you can overall reduce the overall cost of the carbon fiber. So these days a lot of work has been done both by Oak Ridge National Lab as well as many other universities, where they clearly where they use lignin, which is one of the low cost materials, and that way they try, and if they can achieve the same kind of property portfolio with the lignin, then that's a big achievement, because they can reduce the overall cost of the carbon fiber. So carbon fiber has a potential to see a lot of application in the automotive sector, but the high cost that it's associated is what is hindering its widespread application within the automotive field. So they're trying multiple different ways so that they can reduce the overall cost and increase the application domain or application base within the automotive domain. And this is a glimpse of the modulus in the strength as the heat treatment process goes from stabilization to carbonization to graphitization. So some significant applications of carbon fiber are in the automotive, aerospace, spacecraft, racing cars, as well as compressed tanks. Let's look at carbon fiber coating. Just very similar to the glass fiber coating, carbon fibers do have a special coating structure. And if you go and ask a supplier, hey, can I get carbon fiber? The very first question he will ask is what toe size. Toe, as we talked about, it refers to the carbon fiber in each filament, right? You have one filament of carbon fiber, but the toes are available in 1K, 2K, 3K. K refers to the 1000, so it will be 1000 filaments together, 2000 filaments together, 3000, like that. So needless to say, the diameter of 1K is larger, or the 3K. Obviously 3K, right? So you'll have high, of course, if you have 12K toe, the diameters will be very significant, will be very large compared to a 3K. So depending upon your application, whether your application mandates a very thin fiber or a very thick fiber, that's exactly how you need to define the size of your or the type of the carbon fiber you procure.